Hi guys, welcome to my YouTube channel. Thank you for tuning in. Today we're gonna do vertical projectile motion, but I'm just gonna put in my apologies. I'm located at a bit of a busy location today, so you may hear some sounds in the background. Apologies on that, but I'll try to edit it wherever I can so that you can get less distraction, right? Okay, let's get into it. So we're doing vertical projectile motion, which basically is an object that is moving along the vertical axis. So it means moving up or down, right? So when we're speaking or referring to vertical projectile motion, we usually have two instances where we refer to a free-falling object. In this object, the only force acting on the object is gravitational force. That's a free fall. And then we have what we call a projectile. A projectile is an object that has been given an initial velocity and then afterwards moves under the influence of gravitational force only, right? So this one is just gravity only. This one has been given an initial velocity, right? I'm going to get right into the scenarios and the graphs, and then in the next video we're going to do some questions. So there's about 4 main scenarios that you need to know how to differentiate and interpret the graphs for. So when you're having a free-falling object, right, then we can represent the motion of that object. It's usually a ball. We can represent the motion of that object using a position time graph, or a displacement time graph, or a velocity time graph, or acceleration time graph. For today, I'm going to focus on position time, velocity time, and acceleration time graphs for 3 main scenarios, right, of the 4. So the one of the balloon, I'm not really going to focus on. I'm going to bring a question, which is just going to cover it, right? So there's some key words there when you've been given a vertical projectile motion scenario. So for this, for purposes of grade 12 in South Africa, then we deal with objects where gravitational force is the only force acting on that object, even if it's given an initial velocity. So we ignore air friction and all other forces that could be acting on the object, right? So you'll see some keywords. One, we can have a situation where we are told that an object is dropped from a certain height, right? Object is dropped from a certain height. That object can have, let's say you have a balcony and then you have an object that is dropped from the balcony. Then you can be able to draw what we call a position time graph for the motion of the object. So this is position and this is time in seconds, right? From the height that the object is dropped from, then you can draw your position time graph going down until it reaches the ground. So in position time graphs, you can either use the ground as your reference point, or you can use the height that you are throwing or dropping the object from as your reference point. So in this one, my ground is the 0 point. Hence, the graph is, or the motion of the object is gonna end at the 0 point, right? When the position is 0, that's going to be the ground. So it's going to end on the ground. Let's say we just given that part where the object reaches the ground. We're not referring to a bouncing object yet, right? Now, the other important thing here is to note the direction of the object. So you have to choose the direction of the motion. You have to choose a positive and a negative direction, right? From the one that I've drawn, the direction that is positive is above the ground or going up, right? And then going down is negative. So in this specific scenario, up is positive, right? And then you can have another situation for the same graph where down is negative. Then it's sort of like the graph is reflected along the y-axis. So the graph would start here, going in that direction, right? So you can also draw from this position time graph what we call a velocity time graph. So let's say again the object is dropped. What does dropped mean? Dropped means that the initial velocity of the object is going to be 0 meters per second. So it means if I'm drawing my velocity time graph, then my initial velocity is going to be 0 meters per second. And then obviously, since the object is going to be moving under gravitational acceleration only, gravitational force only, then it's going to have an acceleration once I release it, right? So I can draw what I call a velocity in meters per second, time in seconds graph. Now, depending on which direction that was chosen as positive, so we said from this one, up is chosen as positive, which means down is going to be chosen as negative. This ball is going down, which means when I'm drawing my graph here, this graph must start from the 0, since v initial is 0, going down in the negative direction, right? So if I'm drawing my graph, then it should be like this. It's going to be my velocity time graph. If we can say that this is point A, I always say for this VPM, there is nothing that works best than fragmenting, like breaking it up into pieces, having point A to B, B to C, D to E, C to D, like that. It just helps you to get a better picture of the scenario, right? So you can see this is point A when the velocity is 0. This is the position, and this is point B, the velocity with which it's going to reach the ground, right? So you can also have an acceleration time graph. This one is very easy. Let's draw time and acceleration in meters per second squared. For an acceleration time graph, it can either be a positive 9.8 or a negative 9.8 meters per second squared. So depending on the direction that was chosen as positive, right? So if you've chosen up as positive, then down is negative, then it means your acceleration time graph is going to have a negative gravitational acceleration, right? So for this one that I have here, my A would be, I'd put it here, let me label 9.8 meters per second squared, right? So that's for a dropped object. Those are the important things there. And remember, the acceleration is constant. It's not 0, but it's constant, a constant 9.8, hence a straight line graph there, right? Let's move on to the second scenario. Let's move on to scenario 2. Scenario 2, if they say now, in the information you are given, the ball is thrown either from the ground or from a certain height, but is thrown. That's a key word. That means that this ball has a certain initial velocity that is greater than 0. So it's definitely not equal to 0. So if the ball is thrown, let's take the same balcony that we had. Let's take the same balcony we had. And let's say it was just 20 meters above the ground. Above the ground. This is the ground. And then the question now says, draw a position time graph from the time the ball leaves the balcony, thrown from the balcony, until it reaches the ground. So all you're just drawing is like the projectile of the ball. Like from the time it leaves until it reaches the ground, you draw the position time graph. Let's say it's position and time, right? But now what is important again is direction. And what else is important? It's you being able to break it up into pieces, right? So it's going to be thrown. Let's say now we use the ground as our 0 position. Then it's going to be thrown from a certain height, and it's going to reach the ground, right? Okay, that's not very straight. And then what is important here, okay, let's call this point A before I explain what is important. Let's call this point A, point B, point C, and point D. Right, what is important here is what we call time symmetry. So since gravitational force is the only force acting on the object, then the time it takes for the object to go from point A to B and B to C, like from the same position, the time it takes for it to go from the same position and return to the same position is the same. So it means if it took 2 seconds for the ball to go from A to B, then it's also going to take 2 seconds from B to C. We call this time symmetry. It helps you when you're doing calculations, right? Now, another important thing to note is that the ball reaches a certain maximum height before changing direction. We call this maximum height. At the maximum height before it changes direction, the velocity is 0 meters per second, right? So I had said in this graph, okay, so A is when it leaves the balcony, and then you throw it, it reaches a certain maximum height, B, with a velocity of 0 meters per second. When it returns back to the 20 meters above the ground, that's C, and it's going to have the same velocity as it had at A, and it would have taken the same time to go from A to B, B to C, right? And then D is the point when the graph, or rather when the ball reaches the ground, right? So you can also have another situation. I said for this one, ground is the 0 position. Is 0 position. So your graph is going to end off at the 0 position, which is the ground. And then you can have another situation where the ground is not the 0 position. So let's draw it. Now, if the balcony is the 0 position, it means your graph now is going to have to start at the 0 position. So if the balcony is the 0 position, then your graph is going to look like this, right? Then this is A, this is B, this is C, and this is D. So for this one, balcony is 0 position, or it becomes your reference point. That's another way of thinking about it. Right, and then from here you can also draw a velocity time graph. So you can draw a velocity time graph using either one. You can be given either one of the two, and from these two, you can be able to draw a velocity time graph. But now, when you're drawing a velocity time graph, again, you have to be aware of the direction that was chosen as positive, right? So the graph, or rather the ball, is moving from A to B. This is from 0 going up the position, so it's going up in the positive direction. The graph goes from A to B, so it increases, which means up is chosen as positive, right? And then B to C means down is chosen as negative. So when I draw my velocity time graph, it's important for me to know which direction has been chosen as positive. For this one, if your initial direction of the ball is positive, then it means your velocity time graph might start from the positive end of the y-axis. If my initial was the initial direction of the ball was negative, then I would have started my graph on the negative end of the y-axis, right? So since my initial direction is in the positive direction, then it means whatever velocity it's thrown with, which is greater than 0, it's going to start with that velocity at A, right? It's going to start with that specific velocity at A, and then reaches a certain maximum height where the velocity is 0, and then returns to position C, and then continues until position D is reached. So because of time symmetry in this graph, you can be able to indicate a few things. Okay, let's break it up. This is A. This is when it reaches maximum height B. And this is, let's put it around here. May not be that accurate. This is C. And then that would be D. Just don't have space. But D should be a bit further down, right? So from this graph, this is your maximum height. This is C, and D will be further down, but I said since I don't have space, I'm just going to put it here. From this graph, it must be very clear in your labeling of the time. Let's say it had taken 2 seconds for the graph to reach the maximum height, then this would be 2. Then because of time symmetry, this should be 4. And this would be another time depending on how long it took to reach the ground, right? And then again, if you're drawing your acceleration time graph, it's going to be the same as the previous one, because in this instance, up is still chosen as positive. Again, if it had happened that up was chosen as negative, you just reflect the graph along the x-axis. So let me just indicate here in this one, up is positive, right? So if it was the case that up was negative, then this is what you'd have. I'm going to draw it here so that you understand what I mean by the graph is just reflected. I'm going to draw it here. Then this would be A. This would be B. This would be C. And then you'd have your D. It will be looking something like this. Although I'm not giving myself enough space. This would be A. This would be B. This would be C. Yeah, let's put it here. And this would be D. Same graph, just reflected along the x-axis, right? That's scenario number 2. Let's look at the third scenario. Let's say you have a bouncing ball. Let's say you have a bouncing ball. You are given a scenario, bouncing ball. In the scenario, you are told that a ball is dropped from a certain height above the ground, and then it bounces off the ground and then it comes to rest on the ground. Right. So let's say you're given the ball is dropped from a certain height. I'm going to draw the position time first. It's dropped from a certain height above the ground. Right? And then it bounces off the ground. So, sorry about that. So when it's dropped from a certain height above the ground, then when it's in contact with the ground, it also can be very much linked to impulse and momentum, right? So when it's in contact with the ground, there's a force that the ground exerts on the ball, force that the ball exerts on the ground, right? So sometimes they'll take into consideration the time that the ball is going to be in contact with the ground. And sometimes you can get a graph where they don't take it into consideration. So I'm going to do both. Let's say we take into consideration the time the ball is on the ground, right? So they say it's dropped and then it bounces off the ground in contact with the ground for a certain time, then bounces off the ground and comes to rest on the ground. This is again the ground as my 0 point. So now I have to check for direction. In this graph, up is taken as positive. Let's label A, B, C, D, and E, right? So ball is dropped from a certain height, reaches the ground at B, and then is in contact with the ground from B to C, leaves the ground at C, and reaches maximum height at D after bouncing, and then comes to rest on the ground, right? Or you can be given in a situation, usually you are not given the full bounce or the full bouncing motion of the ball, right? So when I'm given like this, then I can be able to draw what we call a position time graph. So it depends on how it's given to you. I'm gonna draw it like this. Velocity and time. So the ball was dropped, so it had an initial velocity of 0, right? So this is now A to B. And then it was in contact with the ground for a certain period of time, and then it left the ground with a certain velocity. Depending on whether the collision was elastic or not, then you can be able to determine the velocity as well, right? So it left the ground at C, reached the maximum height at D, right? And then reached the ground. Let me not use rest. Let's say it reaches the ground after bouncing the first time. So to simplify the explanation, so it reaches the ground, because if I say it comes to rest, then the final velocity is going to be 0, of which we usually don't do such calculations. We do the velocity that it reaches the ground with, which is just before it hits the ground. So let's say it doesn't come to rest, but it reaches the ground after bouncing, right? So the graph can continue after maximum height until it reaches the ground. So if I was to label it, this is point from maximum height to reaching the ground, maximum height to reaching the ground, then it's moving in the positive direction. So that's why the C is now here until it reaches D. Sorry, this is not maximum height, from the height of the balcony, or the height with which it was above the ground. And then reaches maximum height after bouncing, C to D. D is maximum height. And then the velocity with which it returns to the ground, or with which it reaches the ground, at E. Right? That's how you can draw the graph. But let's say you had another situation where now they did not consider the contact time between the ball and the ground. So now, for the same kind of scenario, that's skew. For the same kind of scenario, actually, let's choose the other direction. Let's draw it this side. For the same kind of scenario, right? Let's say now in this specific instance, we had chosen up as negative. So let's say the graph was looking like this, and the ground was your 0 point. Sorry, it shouldn't go past there. And like that. Okay, let's explain what is happening here. This is velocity, this is time, meters per second. This is up taken as negative, right? So if you can see here, then what you are having is the ball is moving from the negative going towards the positive, right? So it's going down, it's going in the positive direction. And then it reaches the ground. So this is A, this is B, this would now be C. B and C would be sort of interchangeable. This is D, and this is E. So to simplify it, we can just call this C and D, right? And then if I was to draw the velocity time graph, can you see now there's no space between the two? So it means they have not taken into consideration the time of contact between the ground and the ball. If I was now to draw a velocity time graph, my graphs are just skew, very skew. But anyhow, if I was now to draw this graph, then it goes with the velocity, initial velocity of 0, right? Going down in the positive direction until it reaches the ground. And then, right, from the ground, it moves from the negative direction, right, until maximum height is reached, and until the ground is reached again. So if I was to label, this is A, this is B, this is still B, right, as far as the position is concerned, and then this is C, and this is D. I already explained that as far as the velocity of B, and this one, let's call it B prime, if they are the same, whether they are the same or not depends on whether the collision was elastic or not. Elastic collision means that the initial and final kinetic energy of the ball is the same. Inelastic means it's not the same. They're not equal, right? So that would depend on whether you have an elastic or inelastic collision. As for the one where you have a hot air balloon, I'm going to cover it as a question because it's similar to the graph that I drew for a thrown object, right? I'm going to cover it as a question. So that's all I'm going to cover for today. I hope you found the information to be helpful. Please subscribe and recommend and bring on all your friends and watch more videos. Just be on the lookout for the one where I do the questions so you can be able to prep for exams, right? Take all the pointers, write everything down, and rewind, ask questions where you need to on the comment section. Thank you for tuning in to my YouTube channel. See you on the next video.